In physics, we measure quantities such as length, time, mass, and temperature, and each quantity measured has its own units. There are lots of different types of units. If you view this on YouTube, in the description below, I'll link to a few videos with unique units, many of which are no longer in use. But there are a few examples of somewhat strange units that are still in use. Some of these are the furlong, which is used in horse racing as a measure of length, the barn, used in nuclear physics as a measure of area, and the banana equivalent dose, used in nuclear physics as a measure of dose of radioactivity, although it is a bit of a joke. To standardize our quantities, we stick to one system, the International System, abbreviated SI. This is also known as the metric system. For length, we use the meter, abbreviated with a lowercase m. For time, we use the second with a lowercase I. And for mass, we use the kilogram or kg. These are the main units that we'll focus on in this course, and they are known as base units. By combining these units, you can make other SI units that are just combinations of these base units. And we will encounter many of these throughout the course. Some other SI units include the ampere, the Kelvin, the mole, the candela, and most of these you will encounter in other courses like chemistry or the second semester of this course. The prefixes listed here on the left allow the same units to express many different scales. For example, we use the millimeter, which is 1/1000th of a meter, and we can use the kilometer, which is 1000 meters, and both of these are multiples of the base unit meter. So this makes the metric system very flexible because it can express such large and such small quantities. If you need a review of scientific notation, I've included a video link in the YouTube description. Something that you'll need to be able to do a lot in this class is to change units or to convert. So to convert between units, we have to calculate a conversion factor. This factor is a ratio of units that is technically equal to unity. So for example, if you wanted to convert 5.5 hours to seconds, then you need to first start by multiplying it by something that converts it to minutes. So how many minutes are there in an hour? There are 60 minutes in an hour, and you choose which quantity is on top by knowing that you want to cancel out the hour. Multiplying this is the same as multiplying by 1 because 60 minutes is equivalent to 1 hour, and when you take that ratio, it's the same as the factor 1. So we can cancel out the hours, and then we want to take minutes to seconds. We know there's 60 seconds in 1 minute, and again we arrange it to cancel out the minutes. We multiply this out to get 19,800 seconds. I want to emphasize here that units can be manipulated algebraically. Again, make sure you write out your conversion factor so that the unit you don't want cancels out and you are left with the unit you do want within calculations. When doing calculations in this class, you'll want to maintain your units within your work. So let's do a simple calculation to show why this is useful. We all know that average speed is equal to distance over time. If we traveled 60 meters in 2.2 seconds, we can calculate a speed of 2.7 meters per second. Meters per second is just like kilometers an hour or miles per hour. That combination of units indicates a measure of speed. So if we wanted to solve for distance traveled, and we are given that we have an average speed of 2.7 meters per second, and we've traveled that for 10 seconds, then we'll start by manipulating that simple equation from above, and we can do that and see that distance is equal to speed times time. We can substitute in our values and cancel out the seconds. So remember now that the units are manipulated just like you do in algebra, so the seconds cancel out and the units we have left over are meters, which is a unit of distance, so that makes sense. But what if you made a mistake when writing down your equation? Let's say you wrote down instead that distance equals speed divided by time. Maybe you're having a hard day. Then we put in the 2.7 meters per second divided by 10 seconds, and we solve and we get 0.27 meters per second per second. Then we think, wait, we wanted a distance. We can manipulate that and see that's meters per second squared. And that is not a unit of distance. So that indicates that we've made a mistake somewhere. Now this is somewhat simple. I mean, you would probably find that mistake pretty quickly. But later on in the class, when we get into more complicated equations, and in further semesters of the class, when there's a lot of different, very complicated units, this will become very useful to check your work. So it's a good idea to go ahead and get into the habit of keeping your units with you at all times. So in this class, you will be expected to have units in all your work in each step, not just at the end. As we're making our way through these videos, pay attention to how I write out the steps to solve the problem and how I always keep my units around. These examples are meant to not only show you examples of applications of the physics we're learning, but also good techniques for writing solutions that can be easily read and understood by your instructor, and that will actually help you look back over the work you did and understand what you've done in the past.